Thanks for joining us today, and welcome to the first of two presentations of our SETI Institute Summer Intern Final Talks. So this summer we had about a dozen students from all around the country, although most were actually from here in California, who spent 10 weeks doing research projects paired up with a scientific member of our research staff as a mentor for the summer. So this morning you'll hear presentations by 5 of those students. The first talk will be by Beth Johnson, who's from San Jose State University. Her mentor was Peter Jenniskens, and her talk is titled CAMS, January through February 2013.
Good morning, everyone. My name is Beth Johnson. I'm from San Jose State University. I'm a senior in physics and astronomy. And I'd like to first ask a question to the audience here. How many of you have seen a meteor? Did anybody go and watch the Perseids the last couple weekends? Yay, so a few of you have. That's really great. Well, I had the privilege of working with Dr. Peter Jenniskens this summer on his CAMS project, which I'll get more into. But this is us celebrating the Perseid meteor shower up at the Fremont Peak Observatory a couple weekends ago. And we're holding a cake because the project had cataloged over 100,000 meteor orbits up to that point. So it was a pretty big deal, and it was awesome because I got to be a part of a team, which is what this summer was about. So you can see a lot of the team members who had helped us out getting this project set up and going. So this summer I worked with Peter on this project. CAMS stands for Cameras for All Sky Meteor Surveillance, and you can see one of the setups here on the screen. Those are 20 cameras. They are low light level security cameras. They take black and white video, and they basically run all night staring at the sky. The purpose of CAMS was to scale up all of the previous efforts for meteor observation. We wanted to bring it to a bigger picture so that we had more meteors cataloged, because basically up until then there were about 7,000 cataloged total. And in 2 years, CAMS has cataloged over 100,000. So the whole point is there's a working list of meteor showers established by the International Astronomical Union. You can see a clip of it here on the bottom. As of July 2013, there were 493 meteor showers in the list. Only 95 had been definitively established. Those are the blue ones that you can see a few of here. And so the point was that we want to validate the remaining 398 showers. There have been a few more since then, but at the moment, this is kind of, you can see it's a huge workload. So when we talk about scaling up, these are 2 of the full setups. There are 3 of them total, so 60 cameras for CAMS. They are located about the Bay Area. One is at Fremont Peak, one is at Lick Observatory, and one is nearby in Sunnyvale. There are also several single CAMs which are operated by amateur astronomers who have volunteered to put their time and money into the project. They cover a huge amount of sky area. So this is actually a graphic of all of the sky that is covered. And you can see the 3 big circles are the 3 main CAM stations. And then the squares, the yellow, white, and purple ones, the purple one actually is inactive at the moment. Those are the single CAMs users and how they help cover the sky. You need at least 2 stations to triangulate the radiant, which is the point from which the meteor appears to be coming at you in the sky. That calculates the orbit back for us. So the more cameras we have looking at the sky, the better our chances of getting those meteors cataloged. Oops. So the heart of CAMS is the software that's running. What happens is you have all these cameras hooked up into computers. The cameras tape all night, and then during the day, the system goes through and takes out any files that have been loaded that don't have any motion detected in them. Every couple weeks, someone goes up to one of the observatories or brings them here on disks, and they're processed here within the office. You have to calibrate them to the night sky. You have to go through and put all of the data into one file so that it can be coincidence later, which is basically someone manually checking through and looking for meteors. One of the really great things about this is that you can actually see, and I use this to figure out what time the night starts and what time it ends. You can see one of the videos from one camera, one single night from January. This is the peak of the quadrantage shower this year, and you can see how amazing the footage actually is. You can see the stars in the background going by, and you can see the meteors streaking across. So what do? I sit at a desk. That's exciting for you, I'm sure. And then I brought all of these disks. These are the 11 hard drives that I use in my work. So the blue ones are all of the cameras brought over from Lick. red ones are from Fremont Peak, and the big black box is everything processed from Sunnyvale. And my job is to put all of these onto my computer and start running this process, which is really, really, really boring. It basically is the one that puts all of the information into a single file, and it takes forever. The fun part begins here, where the program starts to calibrate against the night sky. So the picture on the left is actually the camera image. You can see a meteor streaking in even. And the picture on the right is the map of the sky. So it's actually mapping it out so it knows exactly where everything is. And down at the bottom, it does a calculation to make sure that it's getting enough stars into the field to make it worth the while. The really, really fun part is this. This is where I get to go through and I get to pick out each meteor as it appears on my screen. So in the top left, you have a graph that shows the magnitude versus the distance. So it should always have this sort of peak to it where you see the magnitude increase and then decrease, and it's getting, going across. So I look for that. That's the first clue. The second clue is the bottom left, which is a graph of height versus the downrange distance from a camera. You should always see a downward slope. This is sort of a side cut view of a meteor, so you actually see the line it tracks this way because it's coming in through our atmosphere. The upper right is sort of a longitude and latitude picture from above. It's not real longitude and latitude, it's just sort of a fake map of our own here, but you should see this nice straight line because meteors move so quickly that there's no curve there. And the bottom right is basically where all the information is displayed for me to see things like the radiant and the velocity, and then I also have to take into account these camera offsets, which are sort of a pain. Basically, you have to make sure that all of the computers are set to the same time, and of course, they usually aren't, so you have another piece of little tiny program that you put in the time offsets, and then it can match everything to each other. So in between January and February, I have cataloged almost 6,000 meteor orbits, which has doubled the rate for January for the CAMS project so far. I am currently in the process of looking for outbursts and new showers. You can see on the very top, this is from the CAMS website, and this actually shows you basically the count, the range of the count for each day of January and some of March, which Peter has been working on. We haven't updated February, but I am almost done. And so you can see that quadrantids is the third and how many meteors there actually were that night. There were almost 600. It was pretty fun. And so that's what we're working on, getting this 2013 effort all filled in. So what I did in analyzing these meteor streams is I put together a graph. Now this is right ascension versus declination. And for those who don't know yet, right ascension is basically the point on the horizon that you're looking. So 0 is north, and then you go around clockwise 360 degrees. Declination is the distance from the ecliptic in the sky, so sort of like north and south a little bit. So it gives you the direction to look when you're looking up. So this is all of the meteor streams I got from January. It's a huge mess. You can see the quadrantids is that big black blotch sort of up in the corner up here. And then you can see a couple different things going on. But it's sort of messy and foggy. So we wanted to clean it up. We took into account the Earth's rotation. We put in a nice little formula, and we came up with this. And this cleans up the picture considerably. It's different. It's now lambda versus beta. They don't really mean anything as far as a really good, true measurement. It's just a new mapping coordinate system that takes into account the change in the Earth's rotation. And you can see right along here at 0, across the graph, that it's kind of blank. This is the ecliptic, so you won't see a lot coming at us from here. We have the north and south apex. These are long period comet trails that are left. We have this piece out here. These are all the Jupiter type comets. This is the Helion source. This would be daytime showers, so obviously we can't see them. You can find these sometimes with radar data. And these would be the anti-Helion source, so these come from outside the asteroid belt. And these are just all the streams that we have sort of passed through and collected meteors from here. And we wanted to I wanted to find something new, because that's what is fun about science, finding something new, explaining something that hasn't been explained before. So I focused in on this little red box, and that blotch down there. And I started to say, can I find something, is it cataloged yet? And that's really tough because the list is kind of messy to go through. So I eliminated all these blue circles. Those are known showers. I went through, they're all established, they're all blue on the list, but that red one was still not coming in. So that was when we started to look a little more closely at it. And you can see here that there's a nice little grouping. It's kind of circular, it's clustered up together. And so we think that I may have found a new shower. So it's really, really exciting news for me. Basically, the things that have to be done with that now is tracking it back, making sure these really are coming from the same radiant and that they came sort of in the same time period. We have the data for 7 years of meteor orbits, courtesy of not only the CAMS project, but a Japanese project called Sonatako. So between those, we actually have an even better cluster, and we're going to be going into that in more detail. So we're going to try and confirm our new shower. We're going to analyze the data for other showers because I'm sure you saw there were some more blotches in there that I hadn't ruled out yet, but I was really focused on this one. We're going to work on a paper for it, and I'm also going to finish processing February and March so that we can start working on analyzing that data. I've also decided that I'm going to volunteer to continue helping with the CAMS project because it's such important work, especially with all of the near-Earth objects that we're trying to find. Finding those meteor trails is always really helpful. And those are my references, and I'd like to thank San Jose State University and the Camp Air program for the opportunity to be here. So thank you very much.
And let's use the microphone so that we can capture these on the recording.
It's very nice. So far, did you look at any comet or something being connected to this shower? It's too early for that.
It's too early for that. That is the ultimate goal, though, is to try and find the parent body of the trail that we are looking at. So yeah, that would be even more exciting because if you can find a parent body, then you can associate it, and maybe you can find a comet that hasn't been seen in a while.
Other questions?
What other kinds of moving objects do you see in your video data, and how do you reject them in favor of meteors?
Mostly what we see is clouds, and clouds are a real pain, especially if they're nice and thin and filmy and they wisp across multiple cameras at a time. They're really obvious in the data. Those 3 graphs have to basically be all in that same situation for any meteor to be accepted. And when you see clouds, they're not. You don't get the nice straight lines anywhere. You just see lots of blur and lots of crazy and things. And you also check the velocities. So there's a velocity range between about 11 kilometers a second and about 85 kilometers a second. Anything outside of that is probably clouds, maybe planes, but usually the planes start to go away in the middle of the night.
I have 2 questions. My first question is, my experience in astronomy is only 6 weeks at the radio telescope in Holland when I was an undergraduate. Can you give me a definition, a description of what is a meteor? And the second question is, the units of lambda and beta, are they changed after corrections?
I'll answer your second question first. The units of lambda and beta there really aren't units, it's just a new map. So we don't count them as degrees exactly. They are still kind of degrees, but they're adjusted before solar longitude. So they're not quite the same. As far as a meteor, my understanding is that it is any object that sort of enters at a high velocity from a comet trail generally, or an asteroid trail. It usually makes a bright flare in the sky, and they can pretty much be found all over the planet any time of day. So. But it's just the big bright streaks you see when you look up.
And they're mostly as small as grains of dust, right? Like
Some of them. I'm wearing one. This is a meteorite. This is from China. So they can be bigger. This is actually from a really huge meteorite in China. So it's just a small chunk of it.
Can you quickly go back to the alpha lambda piece? For that one, what's the white streak down the middle?
The white string down the middle is the division between the long period comets and the Jupiter source comets. So it's actually Jupiter perturbs those orbits enough that there's a gap. So Jupiter kind of blocks that area. Those would be the ones that would probably be even more problematic if they were there.
Thank you.
Any other questions? Okay, let's thank Beth again. Great talk. Okay. So why don't you pass the mic over? Yeah, why don't you pass that to Alec? Okay. So, our next talk today is by El-Iza Henson, who's from Sacramento State, and he worked with Cynthia Phillips, who happens to be me.
All right, so my name is El-Iza Henson. I'm from Sacramento State University, and once again, my mentor is Cynthia Phillips. I'll be giving a talk today on Europan topographical analysis using digital elevation maps produced through stereophotogrammetry. So we'll just begin with a summary. First, I'm just going to go ahead and give some Europan perspective. Then we're going to move towards some background in Europa, followed by overview. Then we'll move into the digital elevation maps and stereogrammetry process. Then I'll give you some of my conclusions, some future work, and then we'll be available to ask questions. So we'll begin by just giving some perspective for Europa. As you can see, with every statistic that I have for Europa, I have an analogous statistic for Earth. You can notice that for every statistic on this page, the Earth is significantly greater than that of Europa with respect to surface area, volume, and mass. As we proceed through the statistics for Europa, I just want to bring your attention to the albedo, which we like to think of as reflective potential. As you can see, except for the albedo, once again, the Earth is significantly outweighing and outdoing Europa. This would just be a visual representation expressing the size difference between Europa, the Earth, and the Moon. Something interesting about Europa would just be the color and the surface topography. As you can notice that it differs from that of our Moon with respect to the different numerous craters on our Moon due to the excessive meteor bombardment. Just to move towards the background of Europa, it was discovered in 1610 by Galileo Galilei, along with the other Galilean moons, Io, Callisto, and Ganymede. Currently, astronomers have found 63 other moons, giving Jupiter a total of 67 moons to date. Europa has a 1,250 kilometer diameter iron core, which scientists have been able to detect a magnetosphere. This magnetic sphere is actually induced as opposed to intrinsic like we experience here on Earth. This image is not Europa. The planet, or moon rather, that you see in the background is in fact Io. It just expresses the different previous missions that have already been to Europa. As you can see, Pioneer 10 and 11, the Voyager 1 and 2, along with Galileo and New Horizon. Now, the data that I'll be working with is all from the Galileo mission. So above Europa's iron core exists a silicate mantle, which is essentially just terrestrial rock like that we find on Earth. Above that silicate mantle, we have an icy water crust that ranges from 100 to 200 kilometers, and this ocean is theorized to be the product of tidal flexing. Just to give a little insight as to tidal flexing, that's basically just Jupiter's forces giving kinetic energy to Europa's water and turning this kinetic energy into thermal energy, which basically allows Europa to maintain this liquid core, or liquid interior rather. This visual is basically articulating everything that I just stated. It just gives a good visual to stick in your head. As you can see, it has the iron core, followed by the rocky mantle, and then the icy water crust. It's important to remember that this image that you're looking at is actually an artist rendition. It's not, the exact dimensions are not entirely known. Now we're just moving towards stereophotogrammetry. This is the process that I myself undertook. As you can see, there are two separate vantage or viewpoints of the satellite looking at the same image right here on the terrestrial body. Once we're able to go ahead and get these two images of the same place from two vantage points, our end goal is to actually produce a 3D representation of the surface topography using two-dimensional pictures. These would be two-dimensional pictures that I used. I found these overlapping images, and I just want to bring your attention to the fact that the right image actually overlaps to the left image. And as you can see, I've used the different color coordinate system. You can see the purple here and the purple here, and to the left of that, a darker purple next to another darker purple. This actually helps me see the overlap. When first looking at these images, you can imagine if I didn't have the color system, it would be hard to imagine where does this fit into this. And these ridges, the different ridge lines, are usually what I look for in the beginning process to just help myself get a reference point. Now, at first, we weren't able to produce any images. I'm using 5 vantage points, 4 or 5. However, I decided that if I increase the number of vantage points, that might help the computer triangulate the symmetry between the two areas. And then I moved up to 21 points like we see on this graph. After I collected all of those vantage points, the computer reprojects this image. The difference between these two images and the previous 2 sets of images is the fact that all of the Silex region that's not on this image has been cut out, such that it only has overlapping images with respect to both pictures. After we were able to successfully reproject the image, we were able to produce a digital elevation map. And this is a real critical part in our process. As you can see, I have the first profile line going from left to right, which is one of my conventions. This one is corresponding to this graph right here. And as you can see, we have a distance of 20 kilometers. It's important to realize the vertical aspect of this graph. The absolute numbers that you see on the side, 3,700 to 3,950, are not actually important. We're not articulating that the elevation is necessarily this high. However, what's important is the differentials between the different surfaces. For example, this near 3,750 is about 100 away from this 3,850, and that's what's important, that near 100 to 150 differential in elevation. As you can see, I did the same process with the second profile graph, and as you can see on profile graph number 2, the elevation just slowly increases. After we were able to produce this digital elevation map, we moved on to produce this 3D rendition. This 3D representation of this Silex region is expressed in 2 different color maps. As you can see, we have a grayscale as well as a fully colored. The fully colored map expresses the higher elevations in red, the mid in the yellow, and then the lower elevations are expressed in that icy to dark blue. With a little more experience looking at these images, I was able to go ahead and negate the previous step that I showed you on the last image where I was picking different points of symmetry. I just went straight ahead, and I'm sure all of you can realize this giant crater in the middle known as Silex crater. I just went ahead and used that as my central vantage point, and it became a lot simpler. Once I found it's important to mention that I actually use more points of reference on this image than the last image due to the fact that you see these blocks, these black lapses in data, which are actually overlapping with this very image that I wanted to use as well. As you can see, the computer once again reprojected the image, cutting out all the points that did not overlap with the previous image. After I was able to go ahead and successfully reproduce the image, we have, once again, a digital elevation map. Just want to bring your attention to the central peak at Silex crater. This would be a rather interesting aspect of this region. Graph number 1 goes from left to right, and as you can see, the crater rim vary from the left side to the right side with the central peak at about 300 meters. You can see that our absolute zero is about 100 points from the negative 100, so that gives us a total of 300 meters. As you can see, the crater bottom is roughly level. That's what accounts for this darkened region over here. And this central peak is interesting because it also shows up in my second profile graph, which corroborates the fact of almost 300-meter height. After we analyzed the digital elevation map, we were able to produce, once again, 3D rendition. As you can see, this representation here would be what you would actually see, or near what you would actually see if you were on the surface of Europa yourself. This right region would just be, once again, a color map, allowing you to see the central peak right here in the middle, along with the rim in significant detail. Now we're moving towards my conclusions. After analyzing CX-27, we were able to evaluate that the ridge height ranged from 50 to 100 meters. The ridge length was about 20 or more kilometers. And then we moved on to analyzing CX-25, which would be the crater that we just got through looking at. We were able to determine that from the rim to floor, there's roughly 250 to 300 meter difference. And then that central peak that I mentioned, like I said, was 300 to 350 kilometers. The crater diameter was 16 to 17 kilometers, which accounts for the darkened bottom that I mentioned earlier. And now our future work. The future work that we will undertake is evaluating whether the Helix region and the other surface topography ranges within our hypothesized elevations. And next, we just want to test if my stereogrammetrically obtained data corroborates or contradicts current theorized European surface formation models. Then I just want to go ahead and take a moment to acknowledge, of course, some people that helped me with this process will be Marty Valente and Simone Silvestro, who unfortunately are not in the audience, as well as my lovely mentor, Cynthia Phillips, and Dr. Rudolph, NSF, and the entire REU campaign program. These are some of my references, and now we'll have time for questions.
Nice. In one of the earlier pictures of elevation, the one that didn't have the crater, you had overall slope. And I was just wondering, what did you use for zero surface or level surface for the whole body, like a sphere or an ellipsoid of some sort, or something like that?
So you're asking us what profile, what coordinate system did we use to evaluate? Oh, I see. So we used equidistant cylindrical, which was the surface profile or coordinate system that we use for all of our images, such that we can have our horizontal graph in meters as well as our vertical graph in meters.
Yeah, and these are all, basically we're just doing relative kind of local topography. We're not referencing it to any sort of sort of global 0 point or you know. No, we don't actually. Yeah, it's just relative elevation differences is all we're doing.
So can you assume a level surface for these distances?
Yeah, so for example, on this crater here, probably what we'll do, a further step in the analysis would be to assume that, so see how there's a rim height difference between the left and the right side in that profile one? We would probably tilt it back so that the two rim heights were the same. And that's kind of a further step in the processing as we take more profiles. So that's going to be something we would do later on in the analysis.
Could you say something about the European surface formation theories you were alluding to? Because I was especially curious about your crater. It has this bump in the middle, which is what kind of theory would sort of produce something like that?
So after speaking with my mentor, Cynthia Phillips, we talked about the fact that a unique asteroid, if you will, hit this at a unique angle, which allowed all of the energy to go into producing this central peak, sweeping out all of the other surface topography that you see that's clearly missing.
Yeah, and Europa's weird because it has this relatively thin crust at the surface, and so craters, this is kind of a transitional crater size, anything bigger than this almost blast through that surface layer, and so the craters just become almost totally flattened, or these multi-ring basins with very little topography. So yeah, the craters in Europa are weirdly shallow and have weird flat floors.
I have another topography question. Those ridges in the first map, how are those ridges formed?
So there are different theories as to how are these ridges formed. One theory would be that there is actually a little bit of liquid water under some of these ridges. Due to the minimal amount of liquid water, it's theorized that there's also a little bit of brine mixed in there. Now, when this brine and clear fresh water freezes and then refreezes, the pure ice water actually freezes at a faster rate than the brine water, allowing the brine water to, of course, lock up first, and then once it mixes and freezes with this brine water, it actually expands the ice, allowing different cavities and ridges and semi-quasi mountains to form.
Other questions?
I have two questions. The first one, you just confirm, you just maybe can confirm if Europa has a magnetic field. The other question is that this morning on NPR, the Voyager, about which you talked, is leaving the solar system. One group of astrophysicists, or actually astromagneticians, they are saying there should be a glitch in the magnetic field if the Voyager leaves the solar system. Another substantial group says, no, it should just, you should see nothing. Have you any idea what you should observe when the Voyager leaves the solar system? What happens to the magnetic field?
So if the Voyager left the magnetic field, I actually speculate that there will be no change as well, due to the fact that there is an induced magnetic field on Europa because of the Jovian forces of Jupiter. Jupiter is so significantly more massive and greater than Europa that I'm sure if this little satellite or probe left its orbit, that it wouldn't have any effect on the induced magnetic field that has been there already.
Okay. Any other questions? One more.
So I think your very nice talk has shown me how ignorant I am about Europa and didn't realize I was. I'm aware of maybe a long-standing controversy about whether Europa really does have some moon-spanning subsurface ocean, right? And when you show me things like craters, like if it really was mostly an ocean with ice over it, I don't understand how craters would form or be held on it. So I mean, do we think some of these features tell us that actually there isn't a deep ocean everywhere, or that when you get a crater impact, you're sort of seeing something freezing over and kind of sculpting over a feature of the underlying solid floor below it? Like, I'm having a hard time picturing how it all works.
I see. So, like I mentioned, there's a 100 to 200 kilometer layer of ice that's on top of this theorized liquid ocean. So I imagine, depending on the velocity and the size of the crater, and of course the angle as well, that would determine how deep into the ice it was able to travel. Like I mentioned before, these ridges in different formations you see are actually theorized to be the product of the separation of brine and fresh water.
So we're really seeing a crater that's just made in ice, as opposed to like the ones on the moon where you're seeing what happens when you vaporize a bunch of rock and it kind of settles back in here. You're seeing the effect in ice, which is, I don't know, pretty cool, no pun intended.
Yeah, that would be correct. I imagine you're either seeing a fully iced crater, and if not a fully iced crater, then yes, you are correct. If it was big enough and hit Europa with enough velocity, and there is a liquid ocean, then yes, I imagine it would just be a hole instead of a crater leading straight into Europa's ocean.
Yeah, and we do actually see some of those in some of the bigger craters that we think the impactor has actually gone all the way through the ice layer and sensed the liquid water layer in some way. And one thing to remember about Europa's surface is that, yeah, it's made out of ice, but it's ice at about 100 Kelvin. So basically, it's ice that acts like rock. So it's as strong as rock. It has very similar physical properties to the surface of the moon, which is made out of rock.
Solids are solid.
Yeah.
That's so cool.
This is probably more of a question for Cynthia, but you were saying that some of the larger meteors actually smash all the way through the ice layer. For those ones, how quickly does the ice layer freeze over again?
Well, actually, I imagine that would depend on the temperature and the size of the meteor itself. To elaborate, I'm sure Cynthia will be able to go ahead and do that.
Yeah, so there's no atmosphere. So basically, it's like you're exposing liquid water to a vacuum at 100 Kelvin. So basically, if you did open, say, a crack on the surface all the way to liquid water, or if you did have an impactor that went all the way through to liquid water, you would basically, the liquid would boil and freeze simultaneously until it freezes down to basically till it stabilizes over, so that it stabilizes over the right amount of vapor pressure. And it, very quickly on the matter of, seconds to minutes, you freeze down at least 100 meters or so of ice. So it freezes very quickly.
Even if you've got to get rid of the heat from the impact itself?
Yeah. Yeah, I mean, you might have some very little localized sort of atmosphere over it, but it's not stable for long. It's a really messy process. Okay, let's thank Elle again. Great job. Okay, and so our next talk is by Alec Vinson, who's from Cal Poly Pomona. His mentor was Gorti.
Okay. Hi, my name is Alec Vinson, and my mentor was Gorti. And I'm going to talk today about modeling a protoplanetary disk around the star Teachaw. So a little bit about what T-Tauri type stars are, which is the type of star that we're going to be looking at. T-Tauri stars are a pre-main sequence type star, which means that they're very young. So as young stellar objects, they typically have protoplanetary disks around them. And so this is a little diagram of how the star would form. So you start out with a dark cloud of gas and dust, and gravity makes the gas and dust coalesce into these dense cores. And then gravity can collapse these cores until you get nuclear fusion, and then at that point you have a star. And so you have all this gas and dust that's left behind around the star, and that's going to form a protoplanetary disk. So from this protoplanetary disk, everything starts coalescing until you start forming planets, and then you get a planetary system. So protoplanetary disks can be pretty large, having radii of up to 1,000 AU, and the hottest parts of the disk can have temperatures above 1,000 Kelvin. But most of the disk is very cold at about 20, 30 Kelvin. And they last only about 3 to 5 million years. But planet formation times are thought to occur over time scales of about 3 to 10 million years, which means that the planets are forming as the disk is dispersing. So we're going to study an evolved disk around the star Teachaw. So this is a time that planets would be forming around this star. So we're going to try to model the dust and gas around Teachaw, find the mass distribution and the amount of gas and dust at different locations, the chemical abundances and the size of the disk. And we're going to create model spectra and spectral energy distributions and try to match it to observation. And we're going to also be able to create model images of the dust and images of emission lines, so basically images of different molecules within the disk. And these images could be compared to actual images, which there are some images from a new telescope, Alma, which are going to be released in December that we could look at. And so all this could help us understand disk evolution and planet formation. So T-Cha, it's a T-Tauri type star, so it's a young star, and it's about 100 parsecs away, about 1.5 times the mass of the sun, 1.3 times the radius of the sun, and the temperature is about 5,400 Kelvin. And so it has a protoplanetary disk with a hole of radius 12 AU, meaning just the disk doesn't really start until you're about 12 AU away from the star. And inwards of 12 AU, there's not much gas and dust in there. But it is thought that a planet may be forming within that hole. There's a lot of evidence for that, but it's not conclusive yet. So this is a flowchart of basically what I've been doing all summer. This is a list of different code that I've been using. So I start out with this sigma code, which is going to tell me what the surface density is in the disk. And you have different parameters you can put into that, like the mass and what the density should be at certain points within the disk. And then from that output, you input it into this chakra code, which is going to give you disk structure information. So things like the gas temperature and the dust temperature and the density at each point in the disk. And then you could input that into the chemistry code, which is going to calculate molecular abundances. And so it's also going to tell you what you should see in line emissions. So, if you have, for example, an atom and there's an electron in the atom that's excited to a higher energy level, and then it goes back down, that's going to emit a photon of a specific wavelength, and we could see those in the spectrum, and this code can tell you how much of that you can see. So then you see if those lines match with observation, and if they don't, you start all over again, back to the sigma code, and change some parameters around. And if it does match, then you move on to this RAD-MC3D code, which is going to produce images and plots. So you can make images of the dust in the disk and line emission images or images of different molecules. And you could create SED and spectrum plots. And then again, you see if it matches with observation, and if it doesn't, you have to go all the way back up to the top and change parameters again and go through it all over again. And if it does match, then you have a good model. So these are the results from the sigma and the chakra code. So this is a plot of the dust density in the disk. So here we have the height of the disk versus the radius. How far away you are from the star. So the star would be here at the origin. And then this plot would be mirrored along the x-axis. So right here is the midplane of the disk. So you could see that the disk is more dense the closer you are to the midplane of the disk and the closer you are into the star. And the farther away from the star and the higher up, the less dense it gets. And these are temperature plots. So in the upper left is the dust temperature, and in the upper right is the gas temperature in the disk. So they look pretty much the same. So you assume that the dust and the gas temperature are the same in the interior of the disk. But if you zoom in, this bottom graph here is zoomed into this gas temperature plot, and you could see at the surface of the disk, the gas can get very hot. So here the gas temperature is hotter than the dust temperature. And so then you put that into the chakra code, or into the chemistry code, which is going to solve for a network of about 600 different reactions for 86 different species. And it's going to give you the chemical abundances and then calculates the expected line fluxes that you would see. And so this is just an image, an example of that. You see these different species here, and then what you would expect to see in their line fluxes. And then you would see if that matches with what we've seen. So moving on to the RAD-MC 3D code, you can produce these type of images. So this is what we think the disk would look like if you're looking at 870 micron wavelengths of light. So you could pretty much see all the dust in the disk. And then if you move down to 70 microns, you could still see most of it. And then at 10 microns, you're seeing basically just the inner part of the disk. You're not seeing anything on the outside here. And at 1 micron, you're pretty much just seeing the star, so just a little dot there. And so this is what our spectral energy distribution model plot looks like. So here it's just a plot of luminosity versus wavelength of light. So here we see this kind of shape that corresponds to the star's black body. And then on the right here we have infrared excess, which comes from the disk. So this is all basically coming from the disk over here. And so we could also make spectrum plots. So here we're looking at CO 3:2 transition, and we haven't made a plot yet from our model. We have all the information to do that. We're going to be making a plot this week, but here's just a plot from actual observation. So this is temperature versus velocity, but you could do the same plot pretty much in luminosity versus wavelength, and this is just in velocity because there's a redshift and a blue shift. So part of the disk, if you're looking at the disk, as it's revolving around the star, part of the disk is moving towards you and part of it is moving away from you. So you see a red shift and a blue shift, and that's, so you would expect to see one peak, but since there's that red shift and blue shift, it kind of separates out that peak into two peaks that we see here. So hopefully we would see that in our model when we make that plot. And then we could compare this to future ALMA images too. So ALMA is going to look at TCHA, and we could look at the image of a CO and see if it matches with ours. So this is a quick little overview. So we start out with this sigma in the chakra code, which finds our density and temperature in the disk, and input that into the chemistry code, which can calculate chemical abundances. And then from there, we go on to the RAD-MC 3D code, which gives us images and plots. So understanding these protoplanetary disks is very important to understanding planetary formation. So this is a really interesting image here. On the left here is actually an ALMA image of a different protoplanetary disk. And on the right is an artist representation of what you're seeing. So you can see these kind of streamers that come in from the disk to the star here. And in between, there are these forming planets. So the disk is coming in from, or the gas and the dust is coming in from this disk, accreting onto these planets, and then more gas and dust is accreting from that forming planet onto the star. And it's kind of hard to see in this image, but in this image you could actually see these streamers right here and right here. So, and we hope to see that when we look at TCHA. So, summary of our results here, we got a disk mass of about 0.13 times the mass of the sun, which is pretty large. Disk size about 350 AU. We were able to find different molecular abundances and produce images. And so this method can apply constraints on the disk mass and the size, and by studying these line emissions. And here's some references. Any questions?
Hey, Alex. So I'm assuming the inclination of this disk is nearly face-on to be able to compare to an a model like the one you showed on the previous slide.
The inclination is like 60 degrees, so where face-on is 0 degrees. So it's not quite face on.
Oh, so it's more edge on, so it might be harder to see those streamers if they exist, right, for this.
I mean, you could
for this
probably
guy.
see them, but yeah, I mean, it'd be harder than seeing it on a face on disc.
And so you mentioned that an integral part is sort of it's kind of like you're modeling in a two-step process. You're trying to model the gas first, check that to see if it looks right, the composition and spectra, and then if so, move on to try to model the dust, and then if necessary, repeat. But did you say what data, you mentioned that in the future you'll have ALMA spectroscopy, but what spectroscopic data are you using at this point to check your abundances?
I think it's a combination of different things, like we've looked at Spitzer data and I think Herschel and things like that.
Other questions?
Hi. So what is that? The next slide. What is
slide.
that system called, and what reference lines up with that ALMA image?
I don't remember which system this is. What was the other part of it?
What's the reference that lines up with that?
So
You got a list of
where
references
the
on the
streamers
next.
are?
What's the reference where that came from?
Oh, I think I got it from online from, I think, an ESO website.
Yeah, because that's a really cool image.
Yeah.
Yeah.
Or
Okay.
Yeah, that's a Nature paper by Casassis et al. It's April 2013. So it's on the news. I mean, it's on the ALMA website and it's on the ESO website, because this is what they were hoping ALMA would see, these streamers, because we didn't have the resolution to actually get the sort of information before. And so this was the first such observation that they've made.
And how does this link in with previous theories of planetary formation?
Well, there are holes in these disks that you can sort of tell from the SCDs. Like, for example, Spitzer was the observatory that first discovered that there were these holes in these disks, right? But then you don't really know what's forming the holes. And very often you see the holes in the dust, but you don't know what the gas is, right? And the gas observations have not been sensitive enough to even actually see the lines, forget about imaging them. So this particular case, what happened was that we knew that this disk had a hole, but then there could be a various number of reasons for why you would have a hole. It doesn't necessarily have to be a planet. And the streamers are sort of a conclusive evidence, because you can sort of see that there's a planet. Nothing else could actually produce something like that, which you see. And though the picture looks, the ALMA image itself looks, of course, a lot more rattier than the artist's impression, but that's because this has basically all the velocity information on it. So it's a superposition of different velocities. If you actually look at it in individual velocity channels, you can see the structure much more clearly, but it's difficult to represent that in a single image. So that's basically why it looks like that.
Other questions? Okay, let's thank Alec. Nice job. Okay. You all set? Okay, so our next talk is by Serge Ossipian, who's from Cal Poly Pomona, and he worked with Adrian Brown this summer.
Hello, everyone. Like Cynthia said, my name is Serge Ossipian. I'm an electrical engineering student from Cal Poly Pomona. And this summer, I had the privilege to work with Dr. Adrian Brown. And I'm going to be talking about our project, which is called Metamorphism of Snow Grains within a snowpack in the northern polar regions of Mars. Just a quick outline. I'm going to kind of go through background information, just talking about the basic stuff I'm going to be discussing later on. And I'm also going to talk about how metamorphism of this snow or ice grain works, and also the purpose of the computer model we used to determine these, and also what kind of procedures and steps we took, and what kind of results. What kind of data sets in general we used, and also the results of what we got at the end of it. So first things first, the background information. At this point, we know that on Mars, in the northern polar region, we have two major players of ice parts, I guess, the CO2 and the H2O. And during specific times, the CO2, when the CO2 is present, it's kind of, the temperatures are around 150 degrees Kelvin, so nothing really changes much. But the interesting parts are when the seasons change from spring to summer, when the CO2 evaporates, then the H2O plays a significant role in this ice grain growth. And also, the CO2 disappears differently throughout the latitudes of Mars. And so I'll be discussing at two separate parts mainly on the northern side of Mars. And also, the main player that creates these melting, I guess, are the radiation levels and which creates temperature gradients within the snowpack. The radiation levels, it's kind of, it happens during the clear sky days, and that creates creates radiation level that absorbs, that the snowpacks absorb, and also the albedo level of Mars with the snow on there also plays an integral role on how much light is reflected, so how much heat is kept inside. And these are sensitive, these radiation levels are sensitive to the ice grains and how big they are. And also the infrared heating is different than the visible light because the infrared is absorbed more on the surface level and the visible is absorbed more towards the lower levels, and it's much smaller than the IR absorption. And a little bit about metamorphism. The physical state of snow changes throughout the effects of water vapor diffusion, which is created by the temperature gradients I'm gonna be talking about later throughout the presentation. And during the summer months, there's a lot more water vapor, so that's why we get more grain growth during that time. And the temperature, like I said, the temperature gradients are what cause these water vapors to rise. Quick, easy equation. Not really. Well, I'm not going to get too much into it. I'm just going to kind of show you guys what's the major player here. And pretty much what we're looking here is the temperature gradients, which is this part here. And the Z part is also saying at a different thickness level. So the temperature gradient within different parts of the snow. And also some of the parameters in here discuss also about the mass vapor flux, for example, in this part, which pretty much the two main keys here are the temperature changes and the water vapor changes. All right, down to the model we used. We used a model, a one-dimensional snow temperature model called Syntherm 89, created by CRREL. And this model pretty much is a mass and energy balance model, which is used for computing temperature and energy fluxes within the snowpack. And it was tested in Lassen National Park, which was kind of a precursor for Mars, because we can determine the different temperatures within the layers of the snow. So it was easier to test it here, and obviously it's here, so we don't have to fly up there. And it was pretty successful with that experiment. So that's why we're using this particular model. And the way it works is we have two major input files. One of them called MET, which is standing for meteorological. And what we do is we put in surface temperature, wind speed, and relative humidity on the surface, and just to kind of, and also throughout time. So we have like a long time span, for example, and so we kind of have a profile on the surface. And also the test file, which is more how the surface and everything below the surface is set up initially, like how many layers we're using, which I'm going to show in a picture in a minute, and also what temperatures are each layer's at, and also how thick each section is. And well, this is kind of what it's going to look like when we analyze it. And in the model, we're combining the snow and the ice part, but this is kind of giving you an idea of what it looks like underneath the surface. And what we're doing is we're separating each section, so the snow part, into multiple subparts, I guess, and also the same thing with the soil underneath it. And we use also different levels, so we didn't use, let's say, 10 subparts. We even got up to like 76 in one situation. And before I get into the graphs, I kind of wanted to explain also what the x-axis are all going to be in El sub s format, which is pretty much a format used on Mars because the days are a little bit different than it is on Earth. 1.9 Earth days is equal to 1 L sub s. And the L sub s's go from 0 degrees to 360 degrees. And as you can see, the 0 degree would be the spring equinox in the northern region. So I only took that part because that's what we're going to be talking about. So our changes are going to be somewhere between 0 and 180 pretty much that I'll be talking about more than, well, that's pretty much the only part I'm going to be talking about actually. And this is also a map of Mars in general, and I'll be talking about J numbers. As you can see here, J34 is the most northern part of Mars. So that's one of the points we're going to be talking about. And the other one is going to be around 31, which is somewhere around here. And just to see like how varying it is between those 2 points. All right, so if you guys been upstairs around my table, you've probably seen this on the wall. And this is my wallpaper. And I've experimented with different things. What we're doing is we're taking the initial code and we're just changing small things at a time just to see if we can keep the pattern and see if we can match to the actual results we're trying to get to. So I'm not going to talk about all of them because it'll be too difficult to put them all on here, but I'll kind of show you a few examples of what these graphs are saying. Okay, this is we had some testing SETI GCM points, I think, which were not our final or most accurate ones, but we just wanted to test it just to see how our plots work. And it might be hard to see a little bit, but the x-axis is the time going from left to right in L sub s's. And we're starting around 40 and going up to 110 in this case, almost 110 L sub s. And on the left side, on the y-axis, you see the grain size growth as it's going up in millimeters. And this is significant because you can see how at the beginning, like around this area here, it's starting slowly and then it's going much faster as it goes up, as the seasons are changing from spring to summer. Here's another one we use. This is also another test values. It's not the final one we used, but I just wanted to show you how we're comparing at different levels. This is 33 and 34, not 31, but you can still see how different it is as the most northern part on the bottom is the grain size is growing a little bit slower than the one on the bottom, which is given because the temperatures on the lower, on the least northern part will be changing faster and it'll be getting hotter as well. All right, so in this part, this is where we started getting more serious data in because we were trying to incorporate this initial profile into our model. And this was pretty hard to come up to because we were trying to find the perfect balance because we don't have the temperatures underneath the soil on Mars because we haven't been there, we haven't tested all that stuff out. But we used this model because we were trying to accomplish, we're trying to have more temperature gradients up on the surface, which is what should happen, and this will create a faster grain size growth. And on the y-axis is all temperature kelvins here, so it's going from 185-ish to about 234, and it's also the depth in meters, which is going from 0 to 1 meter on the ground. And these are the actual GCM data that we ended up using. And this is the temperature profile on the surface. And as you can see earlier, I said how the CO2 keeps everything around 150, and you could see that pattern down here. For the light red, it's stopping around a little bit before 50 L sub s, and for the darker one, it's stopping a little bit before 80 L sub s, which is what we want. And also, just to show you how the radiation levels are also changing throughout the seasons. So starting in the spring and going to the summer up here as the radiation levels are going higher up. All right, so this is the data that we came up to recently. This does not look as smooth as we had the previous ones. And there are specific things that are changing here because the profile we use, we're making sure we're using a lot of sublayers. And each sublayer is pretty small. And what's happening here is, as you can see, this jumping a lot. It's going up and then jumping all the way down. What's happening is the top subpartition is disappearing because the grain size is growing, but the melting is faster. So what's happening is once the top one disappears, the bottom one's coming into play, but it doesn't have enough time to kind of get to the pattern where the subpartitions are becoming similar in temperature. So it's doing this jump a little bit. So next step, what we did is we tried to make those subpartitions a little bit bigger or combine them a little bit. Instead of having 76, we kind of shrunk it down to about 25 or 30. And we ended up with something a little bit better, but we could still see some jumping going on. So this is still something we're working on. And I just wanted to show, how this is a little bit more accurate as it shows the CO2 levels as well as the grain size stays within the range that we want it to. And we're initially starting around 50 micron for all the grain sizes underneath the soil. All right, results and conclusions. Our goal was to accomplish the 33 millimeter per season growth, which is the CRISM data results. And we kind of went a little bit over from the results we had earlier. But this is okay because in case we have technicality issues later, it can kind of work for us. But we're still working with the interpretation of the data, and this is not a completed work, but we kind of it's just a step we're going through. And I also wanted to say how the Omega group or team thought that there wouldn't be enough grain growth or enough fast grain growth, so they assumed that it would be something else causing this, but we ended up showing that it is possible to have a fast grain growth. So technically, even at this point, we got a successful result, and I'm sure with more work, we're going to end up having even better results. And I just want to show the references here that we used. And thank you for listening. Appreciate it.
Do we have questions for Serge?
Can you show me the snow compaction equation again, please?
Yeah, that one. Here we go.
We physicists try to understand these equations. Have you any idea why this snow compaction is proportional to t to the power 6? I would maybe expect t to the power cubed or so, or maybe that holy number 7. What are your thoughts about that?
You know what? I read something on there, but I can't remember on top. It's something, I think it's cubed, but there was something square on top of it too. I remember that, and I can't remember specifically what it meant, but I could get back to you on that one for sure.
Okay. My next question is, next summer, what will you do, physics or double E?
I think I'm going to stick to my plan. It's double E with physics minor, so I'm going to try to stick with that. This is fun. This was definitely
when are you going then to change your major?
So we're trying to corrupt you into more physics, right? Okay, other questions? Cool, okay, nice job.
Thank you.
Thanks, Serge. Okay, and our final talk this morning is by Danielle YoungSmith from Barnard College, who worked with Dr. Oana Marcu this summer.
Hi, as Cynthia said, my name is Danielle YoungSmith, and I worked with Dr. Oana Marcu this summer, and I am an astrobiology major and physics minor at Barnard College. This summer, I worked with the algae Chlamydomonas reinhardtii, And we were looking at adaptations to heat stress as a way to figure out how they evolve eventually. And so a little bit of background on this. For astrobiology, in terms of oxidative damage, we're looking at radiation and temperature and desiccation, because those are all different stresses that you get on organisms when you are in space and for life in space. And so this summer we worked on heat shock at 42 degrees Celsius, because that is about the upper limit of what you would expect to find on a habitable planet within the habitable zone of a star. And we also wanted to see a lot of the variations that you could find within these planets. So you look at the heat stress and the different temperatures that they can be at. And we also looked at algae, specifically the Volvocene lineage, because algae is eukaryotic, so it's a lot more complex than prokaryotic bacteria, but it's a lot less complex than, say, an animal cell, or an animal cell, because you want to see actual responses within the cells to the stress that you give them, and that's a lot easier to do with less complex cells. And you want them to be more complex than the bacteria, because the bacteria don't respond in the same way as you would want for life in the universe, the kind of cells that you're looking for that. And our main question for this summer was, is there a common denominator in stress response? And in order to figure this out, you look at different tests, starting at the molecular level and then moving on to the cellular level, and then finally seeing if there is some kind of metabolic change within these based on that molecular and cellular differences that you see within those tests. And then if there is a metabolic change, once you see that and it happens over the course of time and it recurs, then you get an adaptation and then eventually evolution. And that's what we're trying to figure out, if there is a pathway that you can find for evolution of these cells. So we started out with ROS, which is reactive oxygen species, as a signaling molecule. And we looked at this because there is a species called Deinococcus radiodurans, which is actually resistant to radiation and also temperature. And this resistance is permanent resistance. And we know that the Deinococcus had to get to that permanent resistance by going through transient changes and adaptations to the stress response that it has seen. So we tried to see what that kind of transient change would be in the Chlamydomonas that we are working with, and that would be in ROS levels, because the ROS is produced in a cell in response to oxidative stress, and we're looking at the modulations of them. And as you can see on this graph, in the cell palette, you can see a change in the ROS levels, and right at about 120 minutes, 2 hours, you get this return back to the equilibrium level of ROS, and that tells us that the cells that we were working with have gone through some kind of adaptation and are returning back to the equilibrium levels to get back to the normal state, and that is a response to the stress that could turn into something more metabolic and physical. And beyond ROS, we try to figure out how the cells recover and get rid of those ROS levels and break them down. So in order to do that, cells produce SOD and catalase, which both break down the ROS within the cell. And these are enzymes. SOD is superoxide dismutase, and that breaks down superoxide, and catalase breaks down hydrogen peroxide. And both of these are reactive oxygen species. And we wanted to see how these enzymes can break down ROS more effectively. And to do that, we look at the gene expression. And so we use qPCR, which is quantitative polymerase chain reaction, which is basically just amplifying specific genes from DNA and RNA. And when we do this, we can see that there is an increase in gene expression in the heat shock factor and the GPX genes. And so we know that there's something going on within the cell that makes these selectively respond to heat stress. And we also saw this in the copper transporter gene. And this one was very interesting, because we wanted to see why specifically the copper gene had an increase in expression. And to figure this out, we read up on a lot of papers about metals in cells and responses to heat stress. And we found that within these papers, copper mediates ROS levels, and it helps the cells to recover from the reactive oxygen species. And beyond that, cells can take in extracellular metals from their environment and take them into the cell and use them as a way to help respond to the ROS levels, because what they have in their cells naturally is not enough to respond to the ROS. They have to have something bringing it in to help it, because the ROS levels are too high with the kind of stress that we put on them. And so beyond that, once we figured this out, we have to test what kind of metals and where the metals are. So we're on our way to testing for ICP-MS samples. That is inductively coupled plasma mass spectrometry. And right now we just have a ton of samples. We are going to be testing inside the cell, inside the supernatant, and the media for all of these samples to try to figure out where the metals are and in what concentration, and see if there is some kind of connection between those and the cell's response to ROS. And once we have gotten through these are all the cellular and molecular responses that we see within the cell. We want to see if there's a metabolic response, and that metabolic response will help us, would eventually over time help the cell become adapted to the heat stress and be able to evolve to respond to the heat stress a lot better. And so in order to test this, we did PAM fluorometry, which is pulse amplitude modulated fluorometry. Basically, you just shoot light pulses at the cultures and every 1 minute and see how they respond, and map their photosynthetic efficiency over a time period. And so the blue part on this graph is the control. We put it in a water bath at 25 degrees Celsius, which is room temperature. And it's almost straight across, so that is our control. And as you can see below it, the red is the heat shocked one. And the photosynthetic efficiency is definitely decreasing. But the important part to note on here is that right at about 80 minutes, you can see that the photosynthetic efficiency kind of hits a constant, and then it starts to go up a little, so it curves up. And so that kind of is analogous to the ROS response, where there are changes in the levels, and then the cells start to come back up to the equilibrium level, and that is an adaptation. And for both the ROS and the PAM that we did, we were using what we like to call the superculture. That grew incredibly quickly, and we had no idea why. So we put that culture under the microscope and realized that there was a lot of bacteria in it. That is the bacterial culture on the left is our superculture, and the pure culture that we had been growing that grew a lot less quickly was the pure culture with only the Chlamydomonas cells in it. And it was interesting to see because the culture with bacteria actually was a lot healthier, and it had a faster response to heat shock. And so that was interesting, because usually bacteria doesn't give that response. So we tried to figure out if there was some kind of case of this that happened in another culture or another species, and actually there is. And they call it the Black Queen hypothesis, and it occurs in Prochlorococcus, which is a prokaryotic species that lives on the surface of the oceans. And on the surface of the oceans, there is a lot of hydrogen peroxide that occurs naturally. And they found in the Prochlorococcus samples that some of the cells had catalase in their genome and some of them did not. And if you remember from the previous slides, catalase breaks down hydrogen peroxide, and hydrogen peroxide is a reactive oxygen species, which is damaging to the cell. So it was interesting to see that some of these cells that were still alive and still very healthy did not have the catalase, and therefore did not have any response to the hydrogen peroxide. And that showed in this paper that the cells that do have the catalase are actually protecting the rest of the colony from it and removing all of the hydrogen peroxide and making it into levels that the cells can survive at. So they didn't have to do it themselves. And I put the title on here for Keep It Simple, Stupid, because in the paper it talks about a progression towards complexity is the way that most people think about evolution. But it seems that actually keeping everything as simple as possible is probably the best way to go. And it helps cells and grow a lot faster, and they can do it a lot more efficiently. The problem with this case, however, is that Prochlorococcus is a prokaryotic cell, and that whole sample was with Prochlorococcus only. In our sample, we have prokaryotic and eukaryotic cells, so we don't know how that fits in. There hasn't been any kind of case where that has happened. So the next step that we took was to sequence the bacteria to try to figure out what it was and how it is helping our culture. So these are just the steps that we took for sequencing and figuring out the phylotype of the bacteria. And we use the 16S RNA sequence because that part, if you have that sequence, you have a very good idea of what the organism could be, because that is the characterizing primer. And so our results showed that there is a 99% similarity with these three bacteria here, which we have absolutely no idea what they do or what they are like. So we have to do a lot more research on there and try to figure out how they are helping our culture grow. And then just to go back to our original picture, you can see that the bacterial culture is a lot healthier than the pure culture. And the bacterial photosymbionts that we found in the culture are actually helping the cells grow and increasing their resistance to oxidative stress. And then back to our main question, is there a common denominator in stress response? The answer is yes. We found it through looking at the Volvox lineage last summer and comparing that to Chlamydomonas this summer. And with all of our tests for the RAS and metals and looking at the molecular side and then cellular and then finally a metabolic response. And we've seen that that is giving some kind of adaptation to heat stress. And we also found that having a community of organisms is a lot better than just a single organism. Future investigations for this project using radiation as oxidative stress, because radiation is very prevalent in the universe, in space, and that is a large factor in astrobiology and in the stress that organisms experience in space. And then back to the metal part, we want to do a nanopipette in order to figure out where the copper in these cells is located. And the nanopipette is very, very accurate, and the tip is on the order of microns. So it's very, very small, so you can stick it into the cell in any location and determine the concentrations of copper, and obviously you'll know the location from where you stick it. And then finally after that, you can separate the extracellular matrix from the rest of the cell, and there you can actually use it to see whether it actually is binding these metals from its environment and using it to respond to heat stress. And then finally, I had a little side project for this summer also, working with Kepler mission data with Steve Howell. And there have been papers that posit the question of whether there is a relationship between star spot cycles and the orbital period of large planets around those stars in extrasolar systems, because in our solar system, the star has a star spot cycle of about 11 years, and Jupiter has an orbital period of also 11 years. And they think that there might be some kind of correlation between the gravitational effects of Jupiter on the sun and the sun on Jupiter that changes the star spot cycles and the activity of the sun. And so they want to see if there is any kind of case like that in the rest of the solar system based on the Kepler data. And how we did that was to look at the light curves that the Kepler mission is recording, and ignoring the transits of the planets that are around there, we look and see if there's any kind of continuous modulation in which there might be some kind of cycle that we see in there. From the light curve, we make a periodogram through a fast Fourier transform. And if there is one big peak like you see here in the middle, it tells you that there's something interesting to look at. Not necessarily something that we want to see, but in this section, it is basically just the rotation of the star that we see, which usually is about 10 to 25 days. If it's anywhere outside there, it's possible that it is something different, but right now we haven't found anything that correlates to the larger planets that we're looking at and the star spot cycles. It's mostly just the rotation of the star and the different spots on it that keep coming around that you see that modulation. And then acknowledgements. And that was my project for the summer.
Questions for Danny?
Oh, man.
I'm not sure if this is a question for you or your mentor, but you said that you narrowed the bacteria down to one of 3 species. Are you, or is your team interested in identifying which one of those species? And if so, are you using maybe a different gene section, like instead of 16S, would you use 18S or something like that?
So we don't know which of those bacterial species it is. I think we actually have 2 of them in the culture, but right now we haven't done anything. Yes, we will look at the 18S, right?
No, actually,
no? Oh.
There are all 3 of them, so what we want to do next is culture them independently, the bacteria, and separate the rock response compared to mixing the modality. So all 3 of them are present in the different cultures. One of them is involved in integrating aromatic products, another one is methylene and whatnot. We can't use 18S because 18S is used for eukaryotes, so if you want to do anything with algae, then we'd use 18S, but in these cases, there are bacteria, we only use 16S. And it's actually telling us, apparently there are new species because you should get 100% similarity. So you hit a jackpot that you also found new species, so.
That's really cool. Okay, other questions?
Oh, nice projects for the summer. I didn't quite understand the Black Queen reference. It's the title of a book, but I'm curious where the metaphor is coming from. And another question based on that slide: if this, I think it's easy to understand why we're biased towards at least wanting to think of, Carl Sagan's increasing organized complexity that he cited in some of his books. It kind of gives us this feeling that we were somehow inevitable as intelligent life. But since we are at SETI, if a more hard-nosed look at biology tells you that no, actually KISS is the better principle, then where does that leave us? As an accident or merely improbable?
Well, first for the Black Queen hypothesis part, the Black Queen hypothesis refers to Hearts, the card game, where if you draw the Queen of Spades, then you lose the game because the objective of the game is to have as few points as possible. And the Black Queen, the Queen of Spades is actually all of the points added up. So if you draw that, there is no way that you can win the game beyond that. And so that is kind of an analogy to the functions that the cells have. And so in the paper, the cells that are the helper cells, the ones that do have the catalase, are the ones that have all of the functions. And they have the catalase, they have all the rest of the functions that a cell would have. Whereas the other cells without the catalase are the ones that are sort of picking off of the helper cells. And so the Black Queen is basically just all of the functions that you have, and you don't want all of those because they're costly, they take a lot of energy and a lot of resources that aren't necessarily available in the environment. And so that was the analogy that they had. And in terms of keeping it simple, I don't know exactly where it would leave us. I've just seen in biology and in science in general that keeping it simple is usually not where we lead to when we're looking at a project or at any kind of research because our minds aren't wired really to think of the simplest response. It's more to think in depth and to go further. And it seems like some biology is like that too, but I'm not sure.
This may be an area where physicists and biologists differ a bit.
Sorry?
I think that may be a good kind of illustration of how physics and biology are different approaches to understanding the world, because most physics projects really are solid KISS, spherical cows, and it's actually, I think, what turns off a lot of biology students to physics is when they see the simplifying assumptions you have to make to the point that's like, okay, why do I care about this stupid mass on a spring after all, right? So it's one thing to think of it as an approach to problem solving. It's another to think of it as
evolution.
How do things actually work in the specific case of evolution.
Yeah.
So in the case of orthotic, I think a good example that tells you how simple this can get. If you go back to the Volvocene lineage,
you have these organisms that look quite different, and you think, oh, there's so much required, and if you follow through her presentation, there is, you know, PAM and genes and all this stuff happening. But that's why Danny was looking at the common denominator. If you can just look at reactive oxygen species of everything that's required there, so from point A, Chlamydomonas, to point B, Volvox, which is a much more complex organism, it turns out actually that you only need one type of molecule to make that change. Of course, there are much more steps downstream, and it turns out actually also that there are very few genetic changes. So there's not, even though the physiology seems quite complex, the level of the complexity of genomic level is next to null. And all that complexity actually comes from more accumulation of the extracellular matrix mass. And that's why Daniel has been looking at extracellular matrix and metals. So basically, the simple part of evolution in this case would be metals plus extracellular matrix, and that's enough. So I think this is a good example of some sort of biology that looks very complicated until you look really closer and you find that common denominator that Danny has been looking at this summer.
Other questions?
Your Fourier transform of the Kepler data, can you show that to us?
Yes, I can.
It's rather noisy, as you can see. Did you do any filtering, or was it suggested to use maybe another method to get a transform of this time series?
So we did look at doing some phase binning for the light curve part of it just to take out some of the noise in there. However, it takes a lot of time to do that because you are looking at all of the Kepler data for the first 2 years that it was up there. And so it's a lot of data, it takes a lot of time, and as you can see, there was a lot to do in the lab. So we didn't really have too much time to spend on the Kepler.
Natalie Batalla told me that they are also applying maximum entropy.
Sorry?
Natalie Batalla also mentions to me that they are applying maximum entropy, which reduces tremendously the noise.
Yeah, that would be a good one to do. We didn't explore doing that one, no, but that would be a good one. Yeah.
Okay, do we have any other questions? Okay.
Yeah, so for the second part of your talk, you talked about how there's an 11-year sunspot cycle and Jupiter has an 11-year orbital rotation. Are you articulating that there's a correlation or causation? So you're saying that Jupiter's gravity is somehow causing these sunspots, or maybe play a part in causing the sunspots?
Yeah, so that is what we were trying to investigate with the Kepler data. A lot of the papers that we read said that there is a possibility that Jupiter does have some kind of gravitational effect on the sun and vice versa, which changes the way that the sun acts, just because Jupiter is so large that it's the only planet that could have some kind of effect. And for the Kepler objects of interest, we're looking at only stars with planets that are larger than 4 Earth radii, because that would have a gravitational effect on them. And so we're not sure. The only data point that we have is our solar system, and that's why we're looking at the Kepler data to try to figure out if there is some kind of correlation between those two, or if it's just happenstance.
Okay, let's thank Danny, and let's thank all our students for some really great talks this morning. Excellent. And so we've had a fabulous series of presentations this morning, and so join us again on Wednesday morning for 6 more talks by the other half of our students. Thanks a lot.